So now we're going to start our lecture on stoichiometry. That is a really funny word, and it's hard to spell. Good thing you know how to spell it on the test, right? Stoichiometry is an analysis of the relationship between reactants and products in an equation. And let me just copy an equation in here so we can talk about that. All right, stoichiometry. So let's say we have this equation. Propane gas reacts with oxygen, it makes carbon dioxide, it makes water, and we have balanced it nicely. We know that when this happens, 1 molecule of C3H8 will react with 2 molecules of oxygen to make 3 molecules of CO2 and 4 molecules of H2O. Are there any questions about where these numbers came from? And we've got additionally kind of an invisible 1 here. There's nothing there, that means there's a 1 there. These are our coefficients of the balanced equation. Oh, great. Sarah says, I have a question. It's not actually balanced. Nice try, Mary. Good catch. Okay, generally speaking, if you see coefficients, then you know I have balanced it, but this one apparently I've just balanced wrong. So, excellent. I've got the carbons balanced, there's 3 of each. I've got the hydrogens balanced, there's 8 there. But there are 6 oxygens here, plus 4 here, there's 10. So I actually need a 5 here, don't I? Good catch. That was not on purpose. So you guys knew it was not balanced because when you looked at the equation that I gave you, since there were only 2, there's a 2 here, so 2 times 2 gives you 4 oxygens. That made it look like there was just 4 oxygens on the left-hand side. Versus here there are 6 plus 4, so there's 10. So it was, if you think of this as a set of scales, having 10 oxygens on one side and 4 oxygens on the other, those scales would not be balanced. It's kind of one way of looking at it. Okay, so now we've got the balanced equation. Now we have the balanced equation here of the combustion of propane. And we've got these coefficients out in front. And what these coefficients are telling us is that there's a relationship between the amount of propane that I have and the amount of oxygen that it will consume, and the amount of carbon dioxide that it will produce, and the amount of water that it will produce. And you can just see those relationships in the coefficients themselves. So you could say, look, if I burn 1 molecule of C3H8, then I will produce 3 molecules, wow, I could spell, 3 molecules of CO2. And so for the purposes of this equation, it's like those 2 things are equal, because if I've got the one, then I'm going to get the other. I could additionally say that for the purposes of this equation, if I'm burning 1 molecule of C3H8, I'm going to consume 5 molecules of oxygen. And I could even say that if I am burning 1 molecule of C3H8, I will produce 4 molecules of H2O. And I could go on even and look at the oxygen and say, look, if I am burning propane and I'm using up 5 molecules of oxygen, I should expect that I'm going to get 3 molecules of carbon dioxide in my product. And that if I am burning propane and I consume 5 molecules of oxygen, then I could also expect that I'm going to get 4 molecules of H2O in my product. So these are just relationships that I'm pulling out of this equation, and I'm just looking at 2 things at a time. I could even just look at the products and say, look, if I'm burning propane and I produce 3 molecules of CO2, then I can expect I will also have produced 4 molecules of water. I think those are all the relationships in there. Do you see where I got those? Do those make sense? Now, nobody wants to use molecule or molecules because they're too tiny. You can't see them. And so we're going to use a batch, right? Because if 1 molecule makes 3 molecules, then 1 dozen would make 3 dozen. And that means that 1 mole is going to make 3 moles. So I'm going to remove this part here because that's what we really want to deal with. Molecules and atoms are just too tiny, but moles are great. And then we can measure those in grams and convert from moles to grams, and that's convenient too. All right, so all of these conversion factors can be obtained from this one equation as given. Now, you don't need all of them. You just need the ones that you're interested in at the moment, right? So if I said, look, if I am burning 3.5 moles of C3H8, how many moles of CO2 will be produced? Then you don't need to look at the oxygen or the water in this problem because I didn't ask about the oxygen or the water, okay? You can just say I'm burning 3.5 moles of C3H8 and I'm asking about CO2. So really I just need the relationship between C3H8 and CO2. I'm going to presume there's enough oxygen to get me there. I know that water is produced, but I'm not asking about how much of it. So I really only need this one conversion factor. And I'm just going to look and say, okay, 1 will make 3. And so then I can set this up using this new equivalency as a conversion factor using dimensional analysis and say, look, if I'm starting with 3.5 moles of C3H8, and I know that, let's try this. Let's see, 1 mole of C3H8 will produce 3 moles of CO2. And I set it up that way, as you can see, because I want the moles of C3H8 to cancel so that I'm left with the moles of the thing that I want. Then I should be able to get the right answer here. And then I just plug it in. 3.5 times 3. And Sarah got it. That would be 10.5 moles of CO2 that I predict will be formed when I burn my 3.5 moles of C3H8. Does that make sense? Makes sense to Sarah. Anybody else with me? Erica says, would we be given the equation of what you're asking on the test? I'm not sure I understand exactly what you are saying, but generally speaking, we would not be given an equation. All of these are equivalencies that you should be able to pull out of that reaction by observing the coefficients. Now, I would have to give you a reaction if that was your question. Yes. Because all of these equivalencies are nonsense without the equation that's describing what's happening. Otherwise, you're like, no, propane is not the same as carbon dioxide, Mary. You're not making any sense whatsoever. But for the purposes of this equation, in this context, where I say, yes, but if I burn propane, I will make carbon dioxide. So yes, this becomes that, and this amount is functionally equivalent to that amount. Does that make sense, Erica? There will be a reaction. You may have to balance it, but once you have the balanced equation, then you should be able to pull out these coefficients to make any one of these conversion factors that you needed to solve the problem. Okay, let's do another example here. All right, let's say we are given the following equation. And now I'm not going to pull out all of the different conversion factors that I might be able to come from that, but I could just say, let's solve this problem. If we start with 13.5 moles of FeCl3, how many moles Cl2 will be produced in the reaction? Okay, and we can still do our three-step thing. We didn't do it on this last one, but we still can. Step one is to identify what is being asked. What do they want to know? Sarah says, should we reduce, if possible, like 1 Fe equals 1 FeCl3? I wouldn't bother. I think Sarah is saying you can't reduce the entire equation, but if I was looking at just these two, should I reduce them? You could, but I wouldn't bother. I would just leave it as is. She's, I think, just talking about reducing that individual conversion factor. Yeah, okay. But what are we looking for here? Moles of Cl2, perfect. How many moles Cl2? Right there, that's where it is. We want moles of Cl2. Okay, what are we given? Whoops. Yeah, let's see, we're given that we've got 13.5 moles of FeCl3, and then, whoops, because we're interested in Cl2, but we were given FeCl3, then we need to observe just the relationship between the FeCl3 and the Cl2. So we're looking at just these coefficients in front of the FeCl3 and the coefficient in front of the Cl2, and that's where we can see that every 2 moles of FeCl3 will produce 3 moles of Cl2. So that is a conversion factor. And those are the only conversion factors we need here. I'm going to scroll down. So we can set this up. And where am I going to start? Sarah's got the answer, but we've got to verify. All right, Zach says, let's start with our 13.5 moles. FeCl3. And you guys are going to be tempted to drop the moles and just be like, if I've got 13.5 FeCl3s and then I've got 2 FeCl3s for every 3, like I realize that that's really tempting because it's going to feel tedious, but please don't. You're going to want to get into the habit of leaving the identity units as well as the measurement units for everything. 3 moles Cl2 in every 2 moles FeCl3. Perfect. But making sure that you are slow and steady, careful, part of that is just double checking to make sure that you have the identity units of FeCl3 and the measurement unit of mole so that you don't accidentally cancel out the wrong things. So that's it. I got moles of Cl2. I wanted moles of Cl2. It's just one step to go from moles of one substance to moles of another using that equation. So if I plug that in, if I plug that in, 13.5 times 3 divided by 2, get 20.25 moles of Cl2. Does that make sense? They are pretty straightforward. Let's do one more. Let's say let's see. Okay. Let's go back up to this equation right here. We can do another one in there. Some space. Okay. Now let's say how many moles of oxygen are consumed in the reaction which uses 2.25 moles of C3H8. Now, part of the reason I pulled this out for you is because I want to show you that sometimes we might use different language. Here I said how many moles will be produced. Here I'm going to say how many moles are consumed. This is just trying to describe what side of the reaction that it's on, right? So because CO2 is a product, I can say if I start with this reactant, how much product do I get? But because this is a reactant, these two things are going to react together to form those things. So the oxygen will be consumed as it produces these other things. So don't get hung up on this language. You can mostly even just ignore it. And what I want you to focus on is this piece. How many moles of oxygen? 2.25 moles of C3H8. That's like all you need from this description here. So if we focus in on those, then we can note again, step 1, what we're looking for is moles of oxygen. And step 2, we were given 2.25 moles of C3H8. And we've got our conversion factor, which is what? Mole of C3H8 is equal to 5 moles of oxygen. How did you know that, Sarah? Yeah, Sarah just looked at the equation. She's like, there's a 1 in front of the C3H8 and there's a 5 in front of the oxygen, so I knew that 1 is going to be equal to 5. Okay, and that's all we need to set this up. So to set this up, what if we started with 5 moles of oxygen? Can I do that? Yeah, I can do that. I'm going to go backwards because I know I want moles of oxygen, so I'm just going to put moles of oxygen on top where I want it, and then I'm like, crap, how do I get rid of moles of C3H8? What else have I got here? Ooh, look, I have moles of C3H8. I can use those to cancel them out. Just like that. And now my moles of C3H8 cancel. one-step conversion. How do you feel about this so far? Okay, I'm gonna copy this from the worksheet. This back side of your worksheet is all about stoichiometry. And I start with a set of reactions, and I'm asking in section 5, I'm asking specifically about mole-to-mole relationship. So before you can answer these questions, actually, you're gonna have to do something with these reactions here. What do we have to do? We have to balance them. So this is a good throwback to chapter 5. Going to have some practice balancing these equations. So help me out with this first one here. What do I need to do to balance that equation? Got one phosphorus on the left, one phosphorus on the right, so that looks good. And I'll even put this one here to remind myself that I looked at it. Okay. Sarah says, I'm going to need 3 HCls. Why do I need 3 HCls? That seems like a lot. Yeah, PCl3 has 3 chlorines, so I'm going to need 3 chlorines on the right. Okay, so, and I'm doing this last because I've got hydrogens everywhere, so that's kind of not any fun. But I've got 3 hydrogens here and 3 hydrogens here. So that gives me 6 hydrogens on the right. So I'm going to need 3 waters to balance the 6 hydrogens. That gives me 3 oxygens. I have 3 oxygens, so that's, I think that's balanced. Do y'all agree? Okay. All right. What about this guy? Xenon difluoride reacts with water to form xenon plus hydrogen fluoride plus oxygen. All right, since I've got 2 fluorines in xenon difluoride, Nicole and Sarah note I'm going to need 2 fluorines on the right-hand side. I can get that with a 2HF right there. Excellent. Now my fluorines look good. Got a 1 here. Okay. And I actually have 2 oxygens here, but just 1 there. So I'm going to need 2 waters to make that work. Let me put this over here. I'm just going to get rid of it entirely. Going to need 2 waters to balance the oxygens. Okay. That gives me 4 hydrogens, which means, I don't need 2HF. I'm going to need 4HF to give me 4 hydrogens. It's a little bit of a back and forth on this one, but I have faith it's going to work out. All right. If I have 4HF, that gives me 4 fluorines. That means I'm going to have 2 xenon difluorides to balance that. Good eyes. Good eyes. All right, and if I've got 2 xenon difluorides, I'm going to need 2 xenons. Ooh. Did we get it? Done. Whoa. Thank you, ladies. We did it. Was that hard, or was it just like, it was just okay? Medium. You kind of had to go back and forth. It really only becomes hard when you get flustered on the going back and forth, right? If you say, oh, I already changed this and I'm going to change that and it's going to ruin everything, then it starts to seem scary and then it starts to get hard. But if you just say, no, I'm going to change that one. No, I'm going to change that one. It'll come together. It will. Okay, so here we go. That one appears to be balanced. Good. All right, what about this guy? Well, hold your horses, Sarah. I'm not going to make that guy 2 unless I have to make him 2. But if he's got 2 carbons, then I want 2 carbon dioxides. Right? And he has 6 hydrogens, so I'm going to need 3 waters. Right? So I can... There's no reason to make him 2 unless the oxygen says so, and I'm not balancing oxygens till very last because they are everywhere. Right? So... Okay, hang on a second. This is, you're confusing me. One thing that's tricky about this problem is that there are 5 hydrogens plus an extra hydrogen. So be careful to link those together and note that there are 6 hydrogens represented there, because that is really an easy mistake to make. And then when you go backwards, let's see, we have 4 plus 3. We have 7 oxygens here on the right, hopefully. But the other thing to note, and this is easy to forget, that there's an oxygen right here that we can use. So if this is already balanced, that's accounting for 1 oxygen. So 7 is going to equal 1 plus, we need to make that 6 oxygens. So the number in front of the oxygen is going to be what? 3. Perfect. Perfect. Just like that. That one's tricky. It's tricky because the hydrogens are separated, and it's tricky because there's an oxygen in my fuel. But once I account for that, it's just the same as everything else. You balance the carbons, the hydrogens, and you leave the oxygens for last. Okay, good. We've got them balanced. So now we can answer these 3 questions. And each of these questions is looking at, as it says, a mole-to-mole relationship. And so they give me moles of one thing, and they're asking for moles of something else. And again, this question is nonsense without some sort of reaction to refer to. So this is referring to this first reaction here. So to set this up, we can say, look, if I've got 0.15 moles of PCl3 and I want to convert to moles of HCl, what is the conversion factor between moles of PCl3 and moles of HCl? Yeah, we're going to use this 1 mole PCl3 is equal to 3 moles HCl. Okay. Oops. Okay. So when I put this in here, what's going to go on the top? What's going to go on the bottom? Moles of HCl on top. So I'm going to put 3 moles HCl on the top and 1 mole PCl3 on the bottom. And when I do that, that's it. I don't have to keep converting because my moles of PCl3 cancel. And I'm left with moles of HCl, which is exactly what I wanted. So, you know, I could use my calculator, but I could also note that 15 times 3 is 45. I can do that. That's good practice for my brain. 0.45 moles HCl. There's my answer. Should we do another one? Do you guys feel really good about these? Okay, let's do another one. how many moles of xenon difluoride would be required to produce 0.3 moles of HF? So the conversion factor we're going to need here is looking at the relationship between xenon difluoride and HF. What's that relationship here? Yeah, it's 2 to 4. 2 moles XeF2 is equal to 4 moles of HF. All right, and we're looking for the XeF2. So to set this up, oh, and by the way, we were just looking at this equation. So again, this question is nonsense without an equation to reference. And then we say, I'm looking for the relationship between XeF2, and this is the coefficient that I've got, and HF, and this is the coefficient that I've got. And so we see that every 2 molecules makes 4 molecules, or every 2 moles is going to make 4 moles. And this is why we had to balance them first, because we need those coefficients to tell us what the relationship is. Okay, so now Erica says, you could reduce this to 1 to 2, right? Here in that balanced equation, it has to be 2, 2, 2, 4, 1. That's the lowest whole number ratio. But you could certainly reduce that to 1 and 2. You don't have to, but you could if you wanted to, if that satisfies your need for order there. That's totally fine. All right, we can either start with what we're given, 0.3 moles of HF, or we can start with moles of XeF2 because that's what they want. Let's start with what we were given, 0.30 moles of HF. Here we go. And what am I going to put here to get what I want, moles of XeF2? Good. I'm going to put 2 moles of XeF2 on the top. And again, it's going to feel a little bit tedious, but I'm going to put the identity units of XeF2 and the measurement units of HF here. Because if I just said, well, it's a 2 mole to 4 mole relationship, well, moles cancel and I wouldn't know which goes on top, which goes on bottom, right? So I want to make sure that I keep that there. So when I do that, hopefully you see moles of HF will cancel. I'm left with moles of XeF2, which is just what they asked for. So now I could just plug this in. 0.3 times 1/2 is going to be 0.15, right? There we go. All right. These don't take too long. One more. This last one. How many moles of oxygen? So this is number 1. This is what we're looking for, right? Reaction of 1.25 moles of C2H5OH. This is what was given. We're also, because we're given the equation and we can balance it, in that case, we are given the relationship between them, essentially, right? Again, the question is kind of nonsensical without referring to a reaction, and this is the reaction they're referring to. So what's the relationship between oxygen and C2H5OH? Good. It is every 1 mole of C2H5OH is equal to 3 moles oxygen. Good. And that's, again, I'm just looking at these coefficients here. All right, so when I put this together, let's say if I wanted to go backwards and I said I'm looking for moles of oxygen, and here's where I have moles of oxygen. 3 moles oxygen and every 1 mole C2H5OH. Here we go. Whoops, that was not a straight line. Okay, and then how do I get rid of the moles of C2H5OH? I'm going to put 1.25 moles C2H5OH on the top. That was the given amount that I have here. And if I put that on the top, both moles of C2H5OH cancel. And I'm left with my answer. Here we go. 3 times 1.25 gives me 3.75 moles of oxygen. I could have done that in my head. Must have been lazy. Okay. How do you guys feel about these? Definitely need practice, but it's pretty straightforward. Okay, I'm going to give you guys a 5-minute break. We're going to come back and we're going to take it a step further and then a step further after that, okay? So this was kind of our foundation for today. It's going to get gnarly, but we'll come back. We'll do it in 5 minutes. All right, okay, now we're back. And what I've done here was I put the stoichiometry conversation back into that same document where we were doing these molar calculations, because that is our next task. And that is to say that if we can use stoichiometry to tell us about moles of one thing to moles of another, we can take it another step and determine what the mass of that would be, or start from mass. Because that's what we did on Tuesday, right? We did a lot of practice where we said, look, I can calculate the molar mass, and I can use that to convert between mass of one thing to moles of one thing. And now all I've done today is said, look, I can actually take that a step further, and if you know moles of one thing, you can determine moles of another thing. So we're going to put the two together. And essentially, what I'm going to do here is take this little piece that helps me know what to use. I'm starting at moles, and I'm going to add another little piece. And that is, if I want to go from moles of one thing to moles of anything else, A being one thing and B being something else, I just use the coefficients of the balanced equation. Now, I give this to you, I call it a roadmap, because as you can see, if you're starting from moles of something, you can go lots of different directions. And I have confidence that you guys can do each of these equations independently. But what I have observed is that students often will be given one thing, moles of something, and then asked to do a conversion, and they do a different conversion. Because if I said, look, you're going from moles of A to moles of B, use the coefficients, then you'll do that. But otherwise, if I just say convert from here to there, then you might accidentally convert to here because it's something that you feel confident with. Does that make sense? It's like you bolt in the wrong direction, like wild horses. You just it's a conversion. I'm going this direction. So it's like you bolt in the wrong direction. So I'm trying to give you a guidance. I call this the roadmap, so that you can, if you stop and you identify, okay, here's where I'm at, here's where I'm going, then you can make those conversions with ease. And that's what we're doing. So what we did on Tuesday was we did a lot of this, going from moles to grams and back. And what we did this morning is we did a lot of this. We went from moles of one thing to moles of another. And now we're going to put them together. So there's really nothing new here. It's just putting together the things that we've already done. Okay, so let's look at this from the lecture notes. Let's say I'm given this equation. I've got 2 aluminum oxides, and they are going to decompose to form 4 aluminum atoms and 3 oxygen molecules here. And they want to know how many grams of aluminum could be obtained from the reaction of 12.4 moles of aluminum oxide. And when we're done with that, we'll do this other question. Okay, how many grams of aluminum? I don't know, Sarah, we could do any of these, but sorry, I interrupted myself. Sarah says, please don't say that we're not going to go from atoms to moles and then moles to grams. Generally speaking, no. Again, there's just going to be one little question on this conversion on your exam, because once we get to moles, we don't really care about atoms. We're never going to go back to atoms. You can't, there's no scale that's going to weigh out a number of atoms. You can't count them, there's too many. So we just deal with moles and grams almost exclusively. Okay, so, but this is given to you. It's something you'll have to do, and it's something you can do. And so I'm just going to put this here as a reminder that yes, you can do this, but it's not going to get you to grams, right? It's not going to get you to moles of something else. Okay. So how many grams of aluminum can be obtained with the reaction of 12.4 moles of aluminum oxide? Step number 1. What am I looking for? Grams aluminum. Good. Step number 2. What am I given that will help me find what I'm looking for? I'm given 12.4 moles of Al2O3 specifically. And we're given this reaction, which has an equation which shows some sort of relationship between the Al2O3 and the aluminum. What's that relationship? 2 moles of aluminum go to form 4 moles of Al. Good. What else? We're going to need molar mass, because here we've got moles and here we've got grams. So we could calculate the molar mass of aluminum and the molar mass of aluminum oxide. I don't know which one I'm going to need yet, but let's have a look. Aluminum is right here, 26.98. You see that? Aluminium, if I'm British. 1 mole Al equals 26.98 grams Al. 26, there we go. And then we can say Al2O3 has got 2 aluminums plus 3 oxygens, those are each 16. That's going to give me 101.96. Perfect. Thank you, Nicole. Yeah, we got it. 1 mole Al2O3 equals to 101.96 grams Al2O3. So we've got grams all over the place and moles all over the place. We've got to keep our units so we know which, our identity units, so we know which belongs to what. Okay, but I think I've got everything I need to solve this equation. And I can just use dimensional analysis to muddle my way there, but I'm giving you the roadmap, and I want you to use it because it will make your life easier. So let me show you how to use the roadmap. So using the roadmap, I don't know, maybe any more in the area of GPS, like you guys don't know how to use maps. I'm not sure, but like you know, you're in a building and you need to find such and such room, and you're looking at a map, or maybe you're at the mall, right, and you need to find the bathroom. So you look for a map, and essentially it says here's all these places, and you're going to identify, okay, where am I and where do I want to go? 2 questions. Where am I? Where am I going? So in terms of this roadmap, where you are is what they gave you. I am at 12.4 moles of aluminum oxide. And where you are going is what they want, grams of aluminum. Okay, so first we need to define this and say they want grams of aluminum, so we'll call that we'll call aluminum A. And then they gave you moles of Al2O3, we'll call that B, right? Because we've got moles of A and moles of B. Okay, so they gave us moles of B. You are here. And you want grams of A. So this is your destination. Does everybody see how I used the equation as written, assigned which one was A and which one was B, to help me identify where I'm starting and where I'm going? And if I do that, hopefully you can see I'm just gonna follow, this is like a roadmap, right? I'm gonna take this road here to go from moles of B to moles of A, and it tells me how to take that road. It says, get off at the coefficients of the balanced equation, right? Or take the coefficients of balanced equation highway down to moles of A. And once I get that, it says you're gonna take the molar mass of A to get down to grams of A. And then you'll be at grams of A. So this is gonna be a two-step conversion, and this is the direction I'm going. Zach has a really good question, but I'm going to get to it in a couple of minutes, okay? Briefly, he says, how would you know aluminum should be A and aluminum oxide should be B? Actually, it doesn't matter, but I've only got grams of A here. So since this was grams, I said, let's make that A. All right, so if I follow this roadmap, and I've got these conversion factors, then I can get this set up, and I'm going to start with moles of B. So I'm going to actually, this is going to guide me to start from the beginning instead of the end, although I could go from the end. But the roadmap, the way that we use it, we're always going to start from the beginning. So 12.4 moles Al2O3. Dimensional analysis says to take that first step to get to moles of A, I'm going to need the coefficients of the balanced equation. So I come back here and I say relationship between Al2O3 and Al. It's this one here, or it's this one, I pulled it out right here already. So it's good. And I'm going to put the Al2O3 on the bottom so it'll cancel, right? So I'm going to need 4Al on the top and 2Al2O3 on the bottom. And can't forget my moles. I need my measurement as well as my identity units there. And then my moles of Al2O3 cancel. Excuse me. So once we've done this, if we did it right, then we should have arrived at our intermediate destination of moles of A. And in fact, I've got moles of aluminum, which I defined to be A. So I'm sure that I did that right because I've got the right units there. So then it says we're going to take this next step, and you need the molar mass of A to get to the mass of A. And so the molar mass of A, which we said was Al, is going to be right here. And so I'm going to put moles on the bottom so they cancel, right? So that's 26.98 grams of aluminum in every 1 mole of aluminum. And if I do that, then our moles of aluminum cancel, and this roadmap says if I do these two things, then I should be at grams of the thing I said was A, grams of aluminum. That's exactly where I'm at, so I know I did it right. And now I can just plug it in. So we're going to say 12.4 moles of aluminum oxide times 4 moles of aluminum in every 2 moles of Al2O3. Multiply that by 26.98 grams of aluminum in a mole, and I should get 669, grams of aluminum. Right. What I love about this is because, like I said, there's lots of different directions that you could go from here. And you might be tempted, you might accidentally do that, right? We never needed to use this conversion because we never needed to go to grams of aluminum oxide. And so this helped us identify like which of those conversion factors is actually not useful to get me to the destination I was looking for. How do you guys feel about that? Okay, so if we do the same thing, we're going to run another problem like that right here. And you note that we are given step 1. What are we looking for? Moles of aluminum. Yeah, how many moles of aluminum? That's what it says. Okay, 2. And we were given this 38.4 grams of oxygen. Okay, so that's kind of a good start. Before I fill out the rest of these, I'm just going to go over to the roadmap and kind of identify grams is right here, and this is where I've got grams. So I'm going to make this A. It doesn't really matter, but it'll be helpful, right? And aluminum I'm going to call B. Right, so here now we're given grams of A, that's right. And we're looking for moles of B. So we're going to reverse course, reverse position. Your destination is moles of aluminum, so that's up here. And you're starting at grams of oxygen, that's down here. And this says, hey, use the molar mass of A to get here, and then the coefficients to get here. So I only need the molar mass of the oxygen. I'm not going to need the molar mass of the aluminum. That just tells me right there. Okay, if I need the molar mass of oxygen, what is that? Yeah, it peaks oxygen 16, multiply that by 2. We've got 32 grams of oxygen. Good. And then it tells me after I use the molar mass of oxygen to get to moles of oxygen, I'm going to use the coefficients of the balanced equation. What's the relationship here between the aluminum and the oxygen? Four to 3. Perfect. Yep. 4 aluminums and 3 oxygens are made in this equation. So if I make a certain amount of oxygen, I can predict how much aluminum. Okay, so 4 moles Al is equal to 3 moles O2. Good. Alexander says, where did I get the 32 grams? This was just the molar mass. So I looked on the periodic table. I didn't look at the periodic table because I knew that oxygen was 16. Where are you, periodic table? Here you are. Oxygen was 16. So there's 16 grams in 1 mole of oxygen atoms. But because, oh, now I lost my work. Here we go. Because this is the oxygen molecule that comes as a pair, then it's going to be 2 times 16. So that's going to be 32 grams in every mole of oxygen molecules. Yeah. Okay. I think we've got everything we need to set this up. So we're going to start with, you are here, right? We're going to start with grams of A. So that's going to be 38.4 grams oxygen. And my roadmap tells me I need to use the molar mass of A, in this case oxygen, to find the moles of A. So what do I put where? One mole of oxygen in every 32 grams of oxygen. Do note that this method doesn't tell you what to put on top and what to put on bottom, right? You still have to use dimensional analysis to say, if I have grams on top, I need to put grams on the bottom so they'll cancel. But I trust that you guys can do that. Okay, so we've taken this first step of using the molar mass of A. It tells me if I do that, I ought to end at moles of A, and in fact I did get moles of oxygen, which was A, so that's good. So now it says, if you've got moles of A, you can get to moles of B by using the coefficients of your balanced equation. We pulled those out here. So what do I put where? Again, it doesn't tell me what to put on top. You guys have to look at that and say, yeah, we've got to put moles of oxygen on the bottom, so they'll cancel, and that puts the aluminum on top. Good. You got it. So these cancel. So note that these problems, going from grams of one thing to moles of something else, this is just a 2-step conversion. I want you to note this first step here was just a molar mass conversion like we were doing yesterday. The second step here is a mole to mole conversion that we did this morning. We just put it together. And, oh, I've got 2 people who both independently got 1.6, so I'm pretty sure that that's right because they verified. Times 4 divided by 3, wait, divided by 2. Divided by 3. Okay, yes, 1.6. Perfect. How do you guys feel about that? Okay, so I'm gonna go over to our little worksheet. We're gonna look at some mole to mass relationships here. And I'm gonna, it's actually an extension of what we did here. Put it right in here. Okay, but we're still using these same equations here, and now they're kind of messy, I apologize, but I'm gonna post them down here so that we still have them available. Okay, still using these equations for these mole to mass relationships, because again, these questions are meaningless without a reference. So when I say how many moles of water would be required to produce 35 grams of H3PO3, I'm talking about this equation right here that uses water to make H3PO3. Okay, and I want my roadmap still. I like that thing. It's my favorite. I'll sometimes get students who tell me they don't use the roadmap because it looked complicated and confusing. And I think it might at first, but it's just, it helps you so much, I promise. It is worth your time to practice using it. I guarantee it. Okay, all right, so for number one, we're given how many moles of water would be required to produce 35 grams of H3PO3. So we're going to start by saying the first thing that we want, what we want is moles H2O. Yeah, you guys will want to practice. It'll be good for you to practice. But at the same time, if you use the roadmap, it'll help. You won't be quite as overwhelmed. Okay, so we're looking for moles of water. We were given grams of something else. So let's make, if we're gonna go look at our roadmap, grams, we're gonna make this A and this B, right? Grams of A is what I'm starting with. I am here because they gave me that thing. And then moles of something else is my destination. So I'm going to take this route. So it tells me in order to solve this, I'm going to need the molar mass of the A and the coefficients. So great, let's find those. Identify. Step 2. I was given 35 grams of H3PO3. Need the molar mass of A. What's the molar mass of H3PO3? 81.994. I trust you, but I'm just going to check really fast. Phosphorus is 31. Okay. So I've got 31 for the phosphorus, plus 3 from the hydrogens, plus 48 from 3 oxygens, gives me about 82. Yep, perfect. Okay. And then it tells me I'm going to need the coefficients of the balanced equation. So what's that other, what are those coefficients I'm going to need? Yeah, there's a 3-to-1 relationship there, right? You can get, specifically, if you're looking at this equation, 3 moles of water make 1 mole of H3PO3. There we go. Perfect. Okay. So now we can set this up. No problem. And we're going to start here, because this is where I am, with grams of H3PO3. So that's 35.0 grams H3PO3. And my roadmap tells me what to do. I'm going to use the molar mass to get to moles. Okay. Oh wow, I didn't put that on there. So yeah, I want to put grams on the bottom so they'll cancel. Perfect, Sarah. So 1 mole H3PO3 makes 81.994 grams H3PO3. Perfect. When I do that, my grams of H3PO3 do cancel, and I'm left with moles of the thing which I said which was A, so that's good because I should have moles of A out now. So the coefficients of the balanced equation should get me to my destination. We pulled that out here and we said it was a 3-to-1 relationship, and dimensional analysis tells me what moles of H3PO3 on the bottom. So we've got 3 moles of H2O here and 1 mole of H3PO3 here. And if I do that way, my moles of H3PO3 cancel. I'm left with moles of H2O. And when I plug this in, 35 divided by 81.994, multiply that by 3, and I get 1.28 moles of water. Okay. And again, this first part was just molar mass conversion that we did on Tuesday. And the second part was a mole-to-mole conversion that we did this morning. So I'm just putting it together. There's not really anything new here. It's just putting it together, and because there's so many things you can do with moles, you're going to use that roadmap to help guide you so you get where you need to go. Okay. Let's do one more. Just one more, and then we've got to move on to the next section here. We've got to... Okay. So here it says how many grams of oxygen could be produced by the reaction of 2.5 moles of XeF2. So first off, what are we looking for? Grams of oxygen. Good, that's what I'm looking for. And I'm going to say, since that's grams, I'm going to call this A, and that's going to make this B. Right, so in this case, grams of oxygen is what I'm looking for. So that's going to be my destination. And they gave me moles of something else, so that is where I'm at. Does that make sense? I can start from either end of it. I'd go to the other side. Here, okay. So this tells me that if I'm here and I want to go there, the first thing I need is the coefficients of the balanced equation. And specifically, I'm looking for the relationship between oxygen and XeF2. What's that relationship? We've got 1 mole of oxygen in every 2 moles of XeF2. So again, that's just from the coefficients of this balanced equation. There's an invisible 1 here. I can put a 1 there. And there's 2 in front of the XeF2, right? We were also given, of course, that we've got 2.5 moles XeF2. And okay, so if we start here, we use the coefficients, and then we're going to need the molar mass of A, which we said here. A is oxygen. So what's the molar mass of oxygen? (32 grams), that's right. So that's 2 times 16, since each oxygen atom weighs 16. Good, now we can set it up here. And we're going to start with the U are here, moles of XeF2. Okay, so 2.5 moles XeF2. And where do I go from here? What does the roadmap say? Yeah, you guys are right. The roadmap says use the coefficients of the balanced equation. That means we're going to put 1 mole of oxygen on top and the 2 moles of XeF2 on the bottom, so that those will cancel. The moles of XeF2 cancel, and I'm left with moles of oxygen. If I did it right, I should be left with moles of A, and indeed I'm left with moles of the thing which I called A. So that is perfect. Excellent. All right, now what do I do? Perfect. The roadmap says use the molar mass now. So I'm going to use the molar mass of oxygen, right? And it doesn't just say use molar mass, it says use the molar mass of A, because that's what's going to get you back and forth from here. So that's going to be 32 grams oxygen in every 1 mole of oxygen. And if I do that, the moles of oxygen cancel. It's kind of fun, isn't it? Are we having fun? Alexander says, no, this is not fun. Okay, we get 40 grams oxygen. It is work. You guys are right, it's work. But I hope when you get these, if you see a tough problem and you work through the whole thing, I hope when you get done, you feel very satisfied. Like, I did that. I know what I'm doing. This was hard and I did it anyways. We'll get there. We'll get there. Okay. So guys, we need to take it a step further. Because you know from moles of one thing, A, you could go to grams of something or atoms of something or moles of something else. But if moles can do all of these things, then guess what? These moles can also do all of those things. Okay, so here is our full conversions roadmap. This is what is on your exam sheet that you guys can use. Looks like this guy. He is your best friend. All right, because, and this is honestly, it's just mirrored. It does the same thing, because both moles of A and moles of B can do the same kinds of things. And then this is the only way to get from one thing to something else. Again, I know you guys are not excited about this, but I'm not doing anything new in this section. We're going to do molar mass conversions, and we're going to do multimole conversions, and we're just going to stack these conversions. So we're doing more at the same time, but they're the same kind of conversions. Okay. So let's check this out. Here we go. We're given this equation, and I say I've got potassium sulfate. It reacts with barium chloride to make potassium chloride and barium sulfate. This is actually a precipitation reaction, right? Zach previously asked, how did you know that aluminum should be A? And in that case, it's because we were only given one set for grams. But now it doesn't really matter. I can make anything, whatever I wanted, because it's totally reflected here. So I could make potassium sulfate A and barium chloride B, or vice versa. It really doesn't matter. I'll do that. Why not? That's A. There's B. Okay. And when they say mass, that really means grams. So they want grams of A, and they gave you grams of B. So, okay, they gave you grams of B. You are here. They want grams of A. This is your destination. Now, aside from just pulling out all the conversions in the world and puzzle piecing our way there, we can use a roadmap and it'll tell us how to get there. What do we have to do to get from here to there? We're going to need the molar mass. The molar mass of what? We're going to need the molar mass of both. That's right. That's right. Because here it says I'm going to need the molar mass of B to get here, and then to get back here, I'm going to need the molar mass of A. So I'm going to need both of those. All right, so 1 mole BaCl2, it's going to be how many grams? And I'm also going to need 1 mole of K2SO4 is going to be how many grams? I do need both of those. What else am I going to need to solve this problem? The coefficients of the balanced equation, right, to get from B to A. So if I said here that K2SO4 was A and BaCl2 was B, all right, the coefficients here, it doesn't look like there is one, but there is one. It's balanced. There's 1 and 1 and 2 and 1 in that balanced equation. So it's just a 1-to-1 ratio. You should always verify because that is absolutely not guaranteed to be the case. But in this case it was. That was nice. So 1 mole K2SO4 for the purposes of this equation, that's equal to 1 mole BaCl2. All right, and we just need the molar mass of these guys. Oh man, here, BaCl2, I don't even know where my periodic table is anymore. Here we go. Barium, 137.3, ooh, plus Cl2, that's 2 times 35.45. It gets me 208.2. All right. Grams. Good. And then for potassium sulfate, Sarah gives us, it's going to be 170.29 grams, right? And that's 2 potassiums at about 40 each, plus 4 oxygens at 16 each, and then a sulfur, which is, I think it's about 32. That seems right to me. Okay. Oh, and I should specify. That's grams of BaCl2. That's grams of K2SO4. Okay, we have everything we need to set this up, and nothing extra, because we were able to use the conversions roadmap to determine exactly what conversions that we needed. So let's set it up. Where am I going to start? $29.8 grams BaCl2, perfect, because you are here, right? That's my grams of B, perfect. Now what am I going to do with that 29.8 grams of BaCl2? I'm going to use the molar mass of B to convert to moles of BaCl2. Perfect. This one right here, and I need to put the grams on the bottom so they'll cancel. Excellent. So 1 mole BaCl2 is 208 grams BaCl2. Excellent. And once I do that, just double check. Once I do that, my grams should cancel and I'm left with moles of BaCl2. It's always helpful to just make sure that you're still on the route that you thought you were, right? Like if you were traveling down to Las Vegas, you might like double check when you get to Cedar City and double check when you get to St. George, because that's the correct route to take to get to Las Vegas. And if you thought that you'd gone to Cedar City, but you're seeing Logan instead, then that would cause you to double check and make sure that you were paying attention, okay? And reverse course so you get the right answer. All right, so you guys are right. The next step after we got to moles of B is to use those coefficients to get to moles of A. You might be tempted to say, I can skip the step because it's just 1-to-1. But it's not just 1-to-1, it's 1 mole of K2SO4 to every 1 mole of BaCl2. Your units will not cancel unless you put this in here. So even though it doesn't change the number, it keeps you on track for your units. And again, dimensional analysis is all about the units. that should get me to moles of A. We did say K2SO4 is A, and sure enough, we've got moles of K2SO4. So the roadmap says use the molar mass of A to get to grams of A, and we put that right here. And we're going to put the grams on top and the moles on the bottom so they cancel. Looks like you've got that, perfect. So we're gonna put 170.29 grams K2SO4, 1 mole K2SO4, that's it. We are at grams of the things which we said A, and that was our destination, grams of K2SO4. And so now we can just plug it in. And, oh, lost my cursor, hang on. So 29.8 grams barium chloride divided by 208.2 grams of barium chloride in a mole, times 1 divided by 1 times 170.29 grams of K2SO4 in a mole. And I get 24.37 grams of K2SO4. Perfect. What do you guys think? Was that as bad as you thought it was going to be? Again, it is work, it is tedious, but this gram to mole conversion and this gram to mole conversion, that's just what we did yesterday. And this mole to mole conversion is just what we did this morning. So it's all the same things that we've been doing. I'm just putting it together, right? I'm just putting it together. Okay. Let's check out our worksheet here, because we are running a little bit, let's see, low on time. And I spent a lot of time earlier on the earlier stuff because it was foundational, right? I'd rather have you have a really strong foundation and then run out of time at the end, because then you guys can study that end part. But if I rush the foundation, you're going to just be confused. So I would rather do it this way. Okay. We're just going to do this one. So, how many grams of HCl can be produced by the reaction of 59.25 grams of PCl3? Again, this is from your worksheet. And so, in order to answer this question, we're going to need this equation, right? That's on your worksheet. So, according to this equation. And if we leave this, you are here and there's your destination, then I am at, this is going to be B, and here's my destination. It doesn't matter, I could put it the other direction, but it does not matter. And here we go, step 1, what am I looking for? Erica's got a question, is this test longer or less questions? That is a very good observation. Erica notes that some of these problems are just really time consuming. And so for me to fit this test, fit these kind of problems into the test and have them be kind of similar to the test we've seen previously, I either need to give you fewer questions so you can take it in the same amount of time, or I need to give you more time. She's exactly right. She is not wrong. And the answer is I actually make a shorter test. So this test only has 19 to 20 questions on it, whereas your other ones have had 25, 26 questions on them. So there are fewer questions because they do take more time. Yeah, great question. Okay, so what are we looking for here? Grams of HCl. Good. And what are we given here? Let's see. We're given this piece here, right? 59.25 grams PCl3. And then if we're using our roadmap, it's going to tell us if I'm starting here and I'm going there, I'm going to need the molar mass of PCl3, the coefficients, and the molar mass of HCl, right? Okay, we can do that. One mole PCl3 is how many grams? 1 mole HCl. I know this one because chlorine is 35.45 grams plus 1.08, 36.46. You don't have to memorize the periodic table, but if you use it enough, you just remember stuff. And, oh good. We've got 137.32 grams PCl3. That sounds about right. Phosphorus being about 30 grams, and then you've got 3 chlorines. So yeah, plus 31 grams for phosphorus, yeah. Okay, and the last bit we need is we're gonna need the coefficients of that balanced equation. Yeah, so you see a 1 in front of the PCl3 and a 3 in front of the HCl. So 1 mole PCl3 is equal to 3 moles HCl. Perfect. Okay, that is everything we need. And we know that's all we need because we're watching our roadmap. Okay, and I'm gonna actually drag this down so I can give myself more space. All right, so to set this up, where are we going to start? Yeah, 59.25 grams PCl3. And you can go backwards, but just I think using the roadmap, it's helpful to be consistent. So we're just going to start at the UR here and work our way towards the destination. It says we need the molar mass of B to make that happen. What is that? Where do I put where? Good. Molar mass was this one that we calculated right here, and we've got to put the moles on the top. Because we want the grams of PCl3 to cancel. So here, so you can see, I set that up with my dimensional analysis. They cancel. So I'm looking good. And then good. If I'm following the roadmap, I just used the molar mass. I should be at moles of B, which I am. So now I'm going to use the coefficient to get me to moles of A. And we determined that these were the coefficients. 1 mole of PCl3 makes 3 moles of HCl. And I need the 3 on the top. Good observation, so that'll cancel. Good. So if moles PCl3, moles of PCl3 cancel, I'm left with moles of HCl, which I said was A. So I am at moles of A. Perfect. Now to get to grams of A, I'm just going to use that molar mass. And we are at 36.46 grams HCl in every 1 mole of HCl. Go. And then when I plug it all in, 9.25 divided by 137.2 times by 3 times by 36.46. Verified Sarah's answer. We've got 47.2 grams of HCl. Does that make sense? Good. Okay. Lots of practice, and I promise if you use the roadmap, it'll be worth your while. Now there is one last thing that we've got to talk about in the minute we've got left. And that is everything we've done here on paper is what we might call theoretical. And what I mean by that is, I can weigh what I've got and I can predict what might happen and I can calculate what that's going to be, but all of this is what's happening on paper. And what happens in the lab is a little more messy. You guys are taking the 11:15 lab, most of you. You can tell me, does the lab always go the way you expect it to? Do you always get perfect results? Absolutely. Everybody says absolutely not. No, it does not always, maybe even not often, go exactly the way you expect it to. Because maybe you weighed out 59.25 grams of PCl3 very carefully, but maybe you spilled some on the way back to your desk, and so you didn't actually start with 59.25 grams, right? Or maybe you did weigh out 59.25 grams of PCl3, but the bottle came from a supplier and it really was only like 89% pure. So there's not actually 59.25 grams of PCl3 in that container, right? Or maybe you set up this reaction and what happened is that it reacted with something else that was in your flask, like a contaminant. Or maybe it decided it didn't want to react at all, and so you didn't get very much product, right? So what happens in real life is not the same. This means it's not equal to what actually happens. Everybody, I think, understands this as not just a principle for what happens in the lab, but just a principle for what happens in real life. And so we want to know, if I was a researcher and I was publishing a reaction, I would want other people to know what kind of, we'll call it yield, they will expect. Are they going to get as much as they would calculate, or are they going to get a little bit less? And we call that the yield. So the percent, and we give it as a percent. And so here's your equation. Now, I know this feels like, oh no, not one more thing, but this is something you all know how to do. Percent yield is equal to the actual yield, this is what you actually got, that you measured, divided by the theoretical yield, this is what you could have gotten, right, by your calculation, and then you multiply that by 100%, that's what makes it the percentage, okay? So here's a little formula. I'm not going to give it to you on the test. You should know it. But here's how you're going to remember it, okay? Because I know you all know how to do this, because this is just your test score, guys. If I have 20 questions on the test, theoretically, you can get all 20 questions. And then your percent yield would be 100%, and that would be your score. But if instead of getting 20 questions right, you got 18 questions right, then your actual would be 18 divided by your theoretical, which would be 20, and then you would multiply that by 100 to find your grade, right? And you would say, oh, okay, well, 18 divided by 20, that's a 90% grade. And I know that you all know how to do this, because I guarantee you that if you got 18 out of 20 questions on an exam and I gave you 60%, that you would come up and tell me that I did my math wrong. You absolutely would, right? People make mistakes, and you would fact check that to make sure that you were getting the actual grade that you got, right? So that's how I know that you all know exactly how to do it. Just treat it like it's an exam score kind of a thing, and say, okay, this is the number of problems you could get, right? The number of grams that you could get, the number of grams that you actually got, the number of problems you actually got, and then plug it in. So again, this is from the worksheet, just really quickly before I let you go. Oops. If this reaction only produces 37.52 grams, and for the actual, I'd have to tell you, right? Because you're not in the lab. They want to know what the percent yield is. So this reaction was supposed to give me 47.2 grams. It only made 37.52 grams. So how do I calculate the percent yield? Okay, so Sarah took 37.52 grams is the actual, and then she divided that by 47.2 grams, and then she multiplied everything by 100%. And when she did that, she discovered that the percent yield for that reaction was just 79.5%. There we go. Some reactions, obviously chemists like reactions that have very high yields because otherwise you're wasting starting material, and then that also means that you're making a lot of other side products that you have to purify your product from, and that can cause you to lose yield as well, right? So high yield reactions are more well liked, but then again, if you can do something really complicated and get a low yield, that can be better than taking 10 steps at a high yield, because then you lose a little bit every round. So anyways, that's percent yield. That's it. I'm sorry we're a couple minutes over time, but I will let you go, and that is it for this chapter. So I know it is work, but I'm confident that you can do it. So I hope you have a great weekend.